All right, everybody, this is 4.4, the rational root theorem. Basically a way to help us refine our searching a little bit for those real solutions. So in this case, I need to make sure you realize that rational root theorem is only going to help you if you're looking for or finding numbers that are rational, coming from the word ratio. So the rational root theorem will be things like numbers like 9 over 1 or 7 over 5, things where we have ratios of numbers, 2/7, they could be negative, 5/3, whatever, but they have to be rational numbers. You're not going to find any that are irrational, like square root of 17s, or things that are imaginary with the rational root theorem. The only things it's going to help you find are numbers that are rational. So at least though we could get that found and then kind of work from there with other methods. So it's this P over Q thing that you talked about probably last year in advanced algebra, P over Q, where P is a factor of the constant and Q is a factor of the leading coefficient. So when we look at where those numbers are, it's the first and the last numbers when we have it in descending order. Kind of makes sense. Those are the numbers that we always look at when we're solving something by factoring. So we're going to look at those same two numbers with P over Q. So all of the factors that you're going to get will have to be of the form plus or minus P over Q. So all the factors of P divided by all the factors of Q. That'll be the numbers that we should search from if, huge if, the function actually has rational zeros. That's the only ones it's going to help us find. Okay, so let's start with this one. If you want to, go ahead and graph it on your calculator so you can see what the picture looks like, so you can pause to do that. I want you to think about that in connection with what we talk about algebraically. Remember, on the test, you're not going to have a graphing calculator. I want you to know the algebra, but it's not a bad idea for practice right now, for just checking and reinforcing what we know to be true. This is a degree 3 polynomial, so we know there should be 3 roots. At least one of them has to be real. Oh, I don't need to check for that right now. Sorry about that. So at least one of them has to be real, but not necessarily all 3, but they could, or it could be 1 real, 2 imaginary. If it's going to have rational roots, we know we have some numbers we could choose from. Before I even do that, though, look at what I circled. Is it something that we could do easily by factoring? So there's 4 terms. The only thing we know about that is grouping. It's not a good candidate for factoring by grouping. But don't forget to check. Don't assume just because it looks like it's a higher power that maybe we can't factor it. Sometimes you can, so don't make it harder than it needs to be. But I think this is definitely one we're going to have to use P over Q to help us a little bit. So the P value would be the 3, technically negative 3, but we're doing plus or minus anyway when we write the factors. So I'm not going to be super concerned about that, I guess. So it's just the number 3 is what I have to look at, and the number 4. So all the factors of 3, all the factors of 4. And when I do my ratio then for P over Q, I'm going to be looking for all the factors of those ratios. Everybody has sort of their own way of doing this. I like to do 1 over 1, then 1 over 2, 1 over 4, make sure I have all of them, then 3 over 1, 3 over 2, 3 over 4. That's my preference. You guys can decide whatever order makes sense to you for writing those in and making sure that you have all of them. All right, so we have this set of factors that are possible rational roots. So we went from basically infinitely many things that we could guess and check down to only 12, which is a lot better. So when I think about my choices, there's only 12 numbers I have to choose from that are going to be possible rational roots. Now the bummer of it is you still have to try from those 12 and see if they work. And there is a possibility that none of them do, because remember, it's a real solution. There's no guarantee it's rational. But in this one, if you've looked at the graph already, you know that there is one that works, and it's the number 1, which is kind of a nice deal. So we know. So I knew that. But otherwise, it's just random guessing and checking from that list of the P over Qs to see what might work. So go ahead and look at the graph if that helps you to reinforce this first one here. All right, so just going to get my numbers in here and the wonderful 0 at the end, which tells us that x equals 1 is a root of that polynomial. So I know that I have that one real root. Now, if you did look at the graph, you'll know. If you haven't, let's think about what we have left over here. So after you divide, that's going to leave 4x squared plus 2x plus 3, a degree 2. If I were going to keep going, I know I have x minus 1 in this, I would have to take this polynomial and try to factor it into 2 binomials. If you try to do that, it doesn't work, not with real numbers anyway. So how could I find those other 2 solutions? Well, if you've looked at the graph, it's only crossing at 1. This graph only crosses at 1, which means the other 2 solutions have to be imaginary. So we could find those by using the quadratic formula. You guys know how to do that. And then we will get those two imaginary solutions that would go with that. So I know they're going to be imaginary because the graph doesn't cross. I can get those from the quadratic formula. So I've started with the rational root theorem, help me find a real one. Then I can use quadratic formula, this other method, to find those other imaginary solutions. So the rational root theorem kind of gave us that first choice, that first option. Okay, so we're not going to actually do quadratic formula right now. I know you know how to do that. I want to focus today on how we can check those rational ones. All right, so let's try another one. So it says list the possible roots for each equation and then find the rational ones. So here's the polynomial. Again, before we start, think if we could do it an easier way than P over Q. Well, there's 5 terms. We never factored anything like that, so I think we're kind of stuck here. We're going to do P is 15, Q is 2. So I'm going to try all the factors of P divided by all the factors of Q to generate my list of possible rational roots. So again, whatever way you need to do, go ahead, pause the video for a second, write out your P over Q list. So pause, you do it first, then you check with me, whatever order makes sense. All right, so take a look at my list here. I think there's 16 possibilities if I've counted correctly here. So there's 8 of them and plus or minus. We have some fractions and some whole numbers. And if there's going to be a real rational root, it's got to be one of those. So again, we're going to try to guess and check and see if we can come up with some numbers that work here. So I'm going to get my synthetic division ready to go. So if all I'm trying to do here is check and see if I can find a real rational root, basically you could just go through that whole list, try all of them and see what works. So when you do that, you're going to find that actually there are a couple that work in here. So you can guess and check a little bit, pause the video, see if you can find it, or if you kind of want to go in the back door, take a peek at the graph. That might give you some ideas about what numbers you might want to try. But go ahead, pause, try a little bit, see if you can find some real rational roots, then come back and check and see how you did. Okay, so one of the real rational roots for this one was 3. So I'll get the work in here for that one. So make sure you have the synthetic division for the roots that you know work. So that would be 36, that would be 5, that would be 15. We have our magic number 0. Okay, so one of the real rational roots is x equals 3. Now this is a degree 4 polynomial. So we didn't talk about that at the beginning here, but degree 4 means there's going to be 4 solutions. Either all 4 real, 4 imaginary, or 2 of each. Well, we know there's a real solution already, so there's got to be at least one more real solution. We can't just have one. Those imaginary solutions always come in pairs. And if you kept going, now you could start with the polynomial that you have left over and do P over Q with that one. That would eliminate some of the factors, right? Because now the constant is actually a 5 and a 2. So I wouldn't need any of those 3s or 15s anymore. I would just need the 5, the 1s, the 2s, and you could start from there. Or you can just go back to the beginning one. That's totally fine. You can go back to the original and do not quadratic formula, do your synthetic division back from the original again and just keep trying more numbers from your original list. So you always have that option. It really just depends on what you want to do. So the other one that I found was -1/2. Now that's not one that people would like to start with usually because those fraction numbers are a little bit scarier to work on, but it actually works out pretty well when you multiply through to get these. It's not nearly as bad maybe as what you might think when you do that multiplication. We end up getting x equals -1/2 is another real solution. So we have 2 real roots. Now if you looked at the graph, you realize that this graph doesn't cross anywhere else. Those are the only 2 solutions it has. Neither one of them are double roots either. They're not max or min points. So those are the only rational roots that we have. And that's what the question asked us for, right? Determine the rational roots. So we've answered that. If we wanted to find the other solutions, we'd have to take a look at working with the polynomial that's left over and continuing on, which we're not going to do right now. We just want to find the rational ones. Okay, let's try 2 more where we're going to find all the roots now. So we're going to solve, straight up solve. So the difference in the direction here is this is equal to 0. It's asking you to find all the roots, not just the rational ones, all of them. So that means whether they're irrational, imaginary, whatever, we should be able to find them. Again, not a great candidate for factoring by grouping. There's 5 terms. I can't do it the easy way, so I'm going to do P over Q. But when I look at P over Q for this one, I am feeling so much better about it. There's 2 reasons. One, Look at the Q, it's 1. That means no fractions. And then we have a lot less to choose from, and the factors are going to be pretty easy to look at. So when we look at P over Q, it's basically just the factors of P. So go ahead and make your list. It'd be plus or minus 1, 2, 4, and 8. There's only 8 choices for rational roots here. So if I go ahead and set up my synthetic division, don't graph this one, you guys. Resist the urge. See if you can guess and check and find ones that work. There's not that many to try. There's only 8, and they're nice numbers. So go ahead, pause the video, see if you can do synthetic division and find a root that works. And you may find a different one than somebody else might, depending on how many different real roots there are on this one. If there's more than one real root, because remember it's a degree 4, we could have more than one, then you may find something different than somebody else does first. So go ahead, pause, try it. Okay, the one I found first happened to be the 2. Now you maybe found a different one, and that's okay. And that gives us an 8. All right, so if you found a different one first, that's fine. I want to point out those sort of, if you're finding all the solutions, our way of moving forward then. Instead of going back to the original, I know x equals 2 is a root. Instead of going back to the original polynomial now, I'm going to use the leftover. They call that the depressed polynomial. In this case, if this is the constant, degree 1, degree 2, degree 3, it's a cubic. And I'm going to use that leftover polynomial to continue my quest here to find the other solutions. Because remember, for this one, we're supposed to find all of them, which means there should be 4. Okay, so now we have a couple options. Take a look at what you have left. That polynomial, we could do the P over Q again, and we can search, and we can do synthetic, and we can keep going. However, I think this one is easier than that. It's 4 terms. It's a great candidate for factoring by grouping. So you are totally welcome to do P over Q. It works. It'll be great because I know there's some more rational roots, but this one factors by grouping. So that's how I would proceed forward. It's a little bit faster, and it's a little bit less sort of random, I guess, guessing and checking. I know that I'm going to be able to factor it and break it down. So I get x squared plus 4. And then I have my x minus 2 out front. So now I know that I had that original x equals 2. I also have x equals negative 1. Some of you maybe found that when you were searching before, so when you were doing your synthetic division. The last 2 solutions come from this guy. It's degree 2. We could do quadratic formula, but I think this one we can just solve for it, right? What kind of solutions is this part going to give you, though? We're going to get plus or minus 2i. So when I look at this equation and think about what that picture is going to look like, I'm only going to cross the x-axis in 2 places, positive 2, negative 1. The other 2 solutions were imaginary. So I was able to get those factors because I started off with that rational root theorem. It gave me something, and then I could continue on from there. So I guess the moral to this story is you don't have to use P over Q in a situation like this if it's factorable. Go ahead and try to factor it. If it's not, absolutely use P over Q. Okay, one more, solve the whole darn thing. All right, so again, degree 3 this time. Check and see if it's something that's reasonable to factor first. Can we do it an easier way? 4 terms, not a great thing for grouping. So again, we're going to do P over Q, but take a look. P and Q are exactly the same as they were in the last one, right? P is 8, Q is 1. So my list of P over Q is identical to what it was last time. So again, this would be a reasonable difficulty for a test question for sure, because we don't have that many numbers to try, and they're pretty decent numbers to work with. All right, so let's be smart about this. We know we can have up to 3 real roots. We have to have at least 1, right, because it's degree 3, has to cross somewhere. Let's be smart, though. Look at the signs of all the terms. They're all positive. So if you want to get a 0 remainder, and all your terms are positive, what kind of 0 would you have to be trying? Well, you're going to have to use a negative, right? So the only numbers you should really be checking are negative ones, which cuts your list in half for things to try. So try the negative factors and see if you can find anything that works. So go ahead, pause, do your synthetic, see what you can find. Okay, now we have lots of different ones that work in this one, so maybe you have a little bit different statement. So I found the negative 4, which would give me this polynomial left. and I had the -8. Maybe you instead did the -2. If you did the -2 instead, you would have different numbers on the bottom. If you did the -2 instead, you would have had, I think, a 1, a 5, and a 4. If you had found the -1 instead, you would have had a 1, a 6, and an 8. So the polynomial that's left over is going to look a little bit different. But all of the roots are going to be the same. The factors are all going to end up being the same. So I have this right now. Yours might look a little bit different, but ultimately, when I factor to solve this, which it does, you could use quadratic formula, but I sure would pick the easiest way. I'm going to end up with the same 3 factors, hopefully, than what you had as well. So when you look to solve. So this is a situation where once we use that P over Q, we were able to keep going with what was left over and find those other solutions, those other roots. So I have x equals -4, x equals -1, and x equals -2. This one actually has 3 real rational roots. Say that 5 times fast. I'm not even going to try. So we have 3 real rational roots. So we have one at -4, -2, -1. The y-intercept is up here at 8. So think about the end behavior coming up from -infinity, going down, coming back up through that 8, and we have that sort of end behavior. So 3 real rational roots. So P over Q gave us that kind of jump start on the first one. So we had something to start with. Okay, so let's take a look then at the last example so we can make sure we can see all the different possibilities here. All right, so find all possible solutions of this function. So when we're talking about all possibles, it's the same question really as the last ones, except I'm giving you one to start with. So instead of just saying, okay, yeah, here we're starting with nothing and you have to find them, I'm asking you to find all of them when I'm giving you one of them. So I want you to think about the one that I gave you. Take a look at it for a second. This is a degree 3 polynomial that we're going to try to solve and see what makes it 0. So it's a degree 3, so it should have 3 solutions. If you look at the one I gave you, it's imaginary. So what do you know about imaginary solutions? Imaginary solutions always come in pairs. Conjugate pairs, we call that. Conjugate meaning it's the exact same expression except the opposite sign. So when you look at the other 0, it's going to have to be one of the other ones, 2 plus square root of 5i, because imaginaries can never come one at a time. They're always conjugate pairs. So that's awesome. So now I have 2 solutions instead of just 1. I only have 1 left. And what kind of solution does it have to be? If it's degree 3, well, if I have 2 imaginary solutions and it's a degree 3 polynomial, then it has to be real, which is great because I at least have this rational root theorem to help me kind of guess and check some of them. Now, if this real solution is not rational, P over Q is not going to help me at all. But if it is, then I'm going to be in great shape. All right, so P is 18. Q is 1, thank goodness, right? Because that makes life a lot easier. So that means P over Q is just really going to be all the factors of P, whatever that is. So we have 1, 2, 3, 6, 9, and 18. So P over Q, Q is 1, so we just really have those factors of P. So those are the ones we need to guess and check from. I already have 2 solutions. I have the 2 imaginaries. It's just trying to find that one real solution. So if it's rational, this will get me there. So instead of infinitely many to choose from, I've got just that list to choose from. All right, and so you can guess and check. Try doing that. Stop the video for a second. See if you can find that one real solution, and then we'll come back together. All right, so the one that I found was -2. And that would be 8, and that's 9, that's -18, and we get our 0, which is fabulous. So we found that real solution. So x equals -2 is our real root. Thank goodness it was a rational number. So are we done? They said find all the solutions. I have my 2 imaginaries, and then I have my real root, I have my 3. Now, just so you know, when you think about this, what we have left over now, this polynomial that's left, when you look at that, if you solve this, you can't factor it. If you do quadratic formula, guess what solutions you get back to? These guys. right there. Right? So if you do your imaginary solutions, quadratic formula, it will generate those two imaginaries. You don't need to do it because we already know that that's what the solutions are, but that's where they come from. If you did quadratic formula, you get right back to those. So thinking a little bit about what's the degree, what does that mean for your solutions, and then how do I guess and check to try to find good answers is really what we're trying to do for these in section 4.4. So the rational root theorem.